Earthworms shape soil, but beneath the surface of the ocean, their distant cousins survive crushing pressures that warp cells and bend biology itself. Down here, some worms wield jaws strong enough to split fish in half. Others glow, stab, or feed on bone. Why has water forged these creatures into such grotesque, terrifying forms, while landworms remain harmless? The answer begins with an invisible force that redefines life at a molecular level. At depths where sunlight never reaches, water pressure rises by 1 atmosphere every 10 meters, crushing down with hundreds or even thousands of times the force found at the surface. For most life, this invisible weight spells disaster. Proteins buckle, cell membranes stiffen, and the chemistry of life begins to fail. Yet aquatic worms persist, shielded by adaptations that work at the molecular level. Inside their cells, small molecules called piezolites act as microscopic shock absorbers. The most important of these is trimethylamine N-oxide, or TMAO. As pressure mounts, TMAO concentrations soar, rising 100-fold from shallow water to the Hadal trenches, fortifying proteins against deformation and keeping essential enzymes active. Dr. John Yancey, a leading expert on deep-sea physiology, describes TMAO as a molecular cushion, bracing the machinery of life against the squeeze. But pressure does not just threaten proteins. It also targets cell membranes, packing their fatty layers so tightly they risk freezing into glass. To stay flexible, deep-sea worms swap out their membrane fats for more unsaturated types, molecules with kinks that prevent tight packing even under immense force. This chemical engineering keeps their membranes fluid and their cells alive where most would perish. These molecular shields form the first line of defense, allowing aquatic worms to survive where pressure would crush an earthworm flat. Beneath the surface, survival begins with invisible chemistry, long before fangs, bristles, or glowing plumes ever appear. Under the relentless weight of deep water, even the shape of a worm becomes a matter of survival. Elongation is the most striking transformation. Bodies stretch thin, sometimes reaching lengths 10 or 20 times their width, reducing the surface area exposed to crushing forces. This slender design is not just about endurance. It also helps these animals drift or burrow with minimal effort, conserving energy in a world where every calorie counts. Deep-sea worms often shed unnecessary bulk. Their muscles grow sparse, trading power for flexibility. Instead of the dense, rippling musculature seen in earthworms, aquatic species develop a loose, almost gelatinous consistency. This reduction in muscle mass makes them lighter than the surrounding water, allowing them to hover or glide just above the sea floor rather than sinking like a stone. The slow pace of life at depth is written into every tissue. Metabolisms crawl along, conserving energy for rare moments of feeding or escape. Internal organs shrink, and hard parts, if present at all, become thin and fragile. In some species, the skeleton is little more than a thread of protein, barely enough to hold the body together. These changes are not random. They are the outward signs of life engineered by pressure, where chemistry shapes anatomy. The result is a form that looks alien, even monstrous, compared to the compact, muscular bodies of landworms. Here, survival is measured not in strength, but in the ability to yield and persist, reshaped by the invisible hand of the deep. Buried beneath the sand, only a handful of slender antennae betray the presence of one of the ocean's most formidable ambush predators. Eunice aphroditois, known to divers as the bobbit worm, spends its life hidden, an elongated body stretching up to 3 meters, anchored deep within a mucus-lined burrow. The real weapon lies at the front, a muscular, aversible pharynx tipped with 5 chitinous jaws. When prey passes overhead, the worm's antennae sense the faintest vibrations. In a fraction of a second, the pharynx turns inside out, jaws snapping shut with enough force to slice small fish in half. The entire strike unfolds in less than 30 milliseconds, faster than the blink of a human eye. This attack is not just about speed. The bobbit worm's body braces against the walls of its burrow, using the sediment itself as a foundation. Longitudinal muscles contract, channeling stored energy into a sudden forward thrust. Once the jaws clamp down, the worm hauls its victim below the sand, minimizing any chance of escape. Dr. Karen Osborne of the Smithsonian describes the aversible pharynx as a perfect ambush tool, spring-loaded, precise, and nearly impossible to see coming. Unlike earthworms, which rely on gentle burrowing and moist skin for survival, Unus aphroditois is built for offense. Every part of its anatomy, from the reinforced jaws to the anchoring segments, is tuned for explosive violence in an environment where hesitation means starvation. Here, predation is not a secondary trait. It is the defining feature, honed by millions of years of arms races in the dark. On the open seafloor, danger comes from every direction. Some aquatic worms turn their own bodies into weapons, not for attack, but for survival. Fireworms, belonging to the amphinomid group, are covered with rows of bristles called chaeta, each one barbed and hollow, ready to snap off at the slightest touch. When threatened, these bristles break away and embed themselves in the skin of a would-be predator. The pain is immediate and intense. Inside each chaeta, a cocktail of irritant chemicals causes burning, swelling, and sometimes even blistering. Divers who brush against a fireworm remember the lesson for years. The warning is not subtle. Many fireworms are marked with vivid reds and whites, a living caution sign advertising the cost of curiosity. Not all defenses are visible. Some worms in the open water wield light itself as both shield and snare. Pelagic scale worms, for example, are equipped with specialized light organs called photophores. These can flash patterns or glow steadily, confusing predators or luring prey closer. In the deep, where sunlight never reaches, a pulse of cold light can mean the difference between escape and becoming a meal. Some species release glowing mucus into the water, creating a decoy that draws attention away from their own bodies. Others use bioluminescent lures to attract smaller creatures, snapping them up in the darkness. To achieve this agility, pelagic worms often sacrifice muscle mass. Some lose up to half of their muscle tissue compared to their benthic relatives. This trade-off makes them lighter and more maneuverable, able to hover or dart with minimal effort. From barbed bristles that leave lasting pain to light displays that dazzle or deceive, aquatic worms have evolved a dizzying range of tactics to survive. Each adaptation is a response to the relentless threats of open water, a world where being seen, touched, or even sensed can mean sudden death. Near hydrothermal vents, a living tower rises from the darkness. Riftia pachyptala, the giant tube worm, builds a home of chitin and protein that can reach 2.4 meters tall. Instead of a mouth or gut, Riftia displays a crimson plume, an organ packed with hemoglobin, waving in the hot, mineral-laden water. Inside, billions of bacteria thrive. These microbes draw energy not from sunlight, but from hydrogen sulfide spewing from the vents. The worm's blood ferries sulfide deep into its tissues, where the bacteria use it to fix carbon and feed their host. Riftia's entire body is shaped by this partnership. There is no need for a digestive tract. The worm's survival depends on a chemical alliance. In this world, the boundary between animal and microbe blurs, and a worm becomes a living conduit for energy from the earth itself. In 2002, researchers piloting a remotely operated vehicle through the dark waters of Monterey Canyon stumbled onto a macabre scene. The bones of a whale were stripped clean and riddled with tiny holes. Within weeks of the carcass touching down, Osedax worms, later nicknamed bone eaters, had colonized every exposed surface. They lack mouths or guts. Instead, they send root-like tissues deep into the bone, dissolving minerals and feeding with the help of symbiotic bacteria. Dr. Greg Rouse, who helped describe the genus, called Osedax a specialist in using what nothing else can. Their ability to invade and digest bone within weeks reveals a level of adaptation unseen among landworms. In the deep, even skeletons become a niche, and worms evolve to fill it. Out of sight, aquatic worms evolve at the frontier of biology, adapting in ways we barely comprehend. As deep-sea exploration accelerates, each discovery forces us to question what life is truly capable of becoming. The next monstrous adaptation may already be unfolding, unseen and inevitable. Share your thoughts below.